Hi, we'll talk about the code that backs up some of the ideas discussed in this post on reducing popularity bias or selection bias by causal debiased ranking. So we'll we'll start with when we look at the code, we'll start with a current formulation of how people do ranking. We'll see how position debiasing has been done in the state-of-the-art industrial systems. Then we'll extend the idea to use debiasing of user only and item only probabilities. You should read the post to understand why that is done. But here in this video, we'll only look at the code walkthrough. And once we have added the capability to develop probabilities of conversion only based on user and items, then we can use it to debias the signal or the gradient that is coming into the actual neural network. So this part that you're seeing that has all the features, you still have that here, but the gradient that is coming back has been debiased from the other logits. So that's what we'll code up. And then you have this mixture of logits aspect, which looks at the features and figures out how much importance to give to each of the sources of explanation. So think of this final logit that we are sending out as we are trying to explain the observed behavior, and some part of it is explained from user-only tendencies. So maybe this is a user who is maybe you're building a podcast recommender system, and this user just listens a lot. So this probability will be higher. And as opposed to that, some other user listens very less, like they have very low conversion. So that part of um, the bias or the tendency of the user is captured through this user-only logic. Similarly, if there are popular items or high conversion items or low conversion items, that's captured here. And the remaining aspect is captured by personalization, basically. Okay, so and then you have this mixture of logits that learns how much importance to give to each. And finally, we look at how to anchor the user only and item only and position only logits by separate gradient. So let's get into the code. I sort of explained the same things in the README, and I've linked them to the respective files. So first, we'll have a multitask estimator. This is more your run-of-the-mill ranking system, which takes all the features and tries to estimate the T task labels and learns them by cross entropy. And then we'll progressively encode what we mentioned in the post. Okay, so the tests are in tests and the code is in sources. The multitask estimator, you have the initialization. Among other things, it creates the torsion and embedding just so that it can process user ID and item ID. Then it sets up the sequential architectures for processing user features and item features and cross features. And finally, this is the architecture that finally outputs the task probabilities. So let's dive into the forward function. This calls process features, which first use the torsion and embedding to go from user ID to an embedding. Same for item ID. It transforms the user features through the architecture, user features layer created above. At the end of it, for instance, let's take the user side, user embedding and user features transformed are both dense inputs. Now, I think of the same dimension. I've set it the same dimension. You need not have it the same dimension, but that's what I've done it here. And after that, same from the item side, and similarly processed the cross features. Then we concatenate all of them So these are all then processing of the input features, combine them, and these combined features are passed through a task arc, which outputs the T probabilities of the T tasks for each item in the batch. That's it. So this is what your normal ranker does. It comes up with a probability of observing the T conversions, which you can then use in your value estimator, whereby maybe you have some weights for each of the task labels that you can combine these with, and then the combined score is what you sort. So I've done that here in the top item selector. This is sort of a schematic of how people do multitask ranking. So this initializes this estimator, and in the forward function, I'll go into this detail later, but let me just walk you through what it does. In the forward function, it calls the estimator to get the T task labels. Then it combines them by weights that have been separately learned, which are sort of the importance of each of the task labels. And this combined score is what you sort based on. Here I'm just choosing one item and taking an argmax. If you want to sort and select, like, let's say 5 items, you can change this. Let's look into the part before that a little bit. So the input to this ranking mechanism is you have one user ID, user features, but you have, let's say, B item IDs corresponding to each of the items that you want to select the top from. Similarly, item features are B. For each of the items, basically, you have II dimensional item features, IC dimensional cross features. So it's one user, B items. That's why you have to sort of convert these into tensors and replicate the user and features B times. So now you can create a batch where each item in the batch is for one item. So the entire batch is for the user, but for you replicated the user features in B times, so that each row in the batch corresponds to one user and item pair. And then we find estimates, the task estimates, and then we score them. So far we talked about the multitask estimator, which creates various ways of processing the features and then passes them through a neural network. And the forward function comes up with T estimates corresponding to the tasks. Then we saw how to use them in the top item selector, which calls these estimates and combines them using externally found out hard-coded user value weights, and then picks the top one.